Okay, picking up where we left off. The atomic mass scale and average atomic mass. And technical problems here. Okay. There was an international agreement. I wasn't there for it. No one asked me. The atomic mass is expressed in atomic mass units, created AMU. It's defined as a mass exactly equal to 1/12 the mass of one carbon-12 atom. Take a specific isotope of carbon, 12. It says 1 AMU is equal to 1/12 of a carbon atom. I don't know. What was it there? I didn't see the minutes of the meeting. I think it's because carbon-12 is plentiful. It was easy to measure at the time, and that seems like a good one to pick. So, doing experiments to show that a hydrogen atom is only 8.3985% as massive as the carbon-12 atom. So the carbon-12 atom, by definition, is 12 AMU. So the atomic mass of hydrogen must be 8.3985% of that, or 1.0078 AMU. If you look at the periodic tables in your book, it's 1.008. More expensive ones have it to a higher degree. Use the number in your periodic table in your book. So if you look at the mass of carbon in the periodic table, it's not 12, it's 12.01. That's because carbon exists as isotopes. And if you take carbon-12, it's about 98.93% in nature. Carbon-13 is about 1.07%. So you do what's called a weighted average. You take the percentage and multiply it by the weight of the isotope, then add the two together. They come out with 12.01. So the atomic masses in the periodic table are average atomic masses. Sometimes we use the term atomic weight. So if you were to look at chlorine 35 and chlorine 37, which are both isotopes, 35 is there around 75%, and the 37 there is around 25%. So to figure out the average atomic mass, it would be 35 times 0.75, and whatever that is. $26.25, and then it'd be 37 times 0.25. $9.25. Add them together, 35.5. And if you look on your periodic table, it's listed as 35.45.
That is the atomic weight.
Pardon?
That is the atomic weight.
Yeah, if you look at your periodic table for chlorine, it's 35.45. And I kind of guessed at the two abundances, so it's not really 75 and 25, it's like 75 point something. But that's how they do it. It's a weighted average. You've all done weighted averages. A lot of instructors use weighted averages. Their tests are worth 40%. You know how to do it. Well, how do you know there were isotopes? Well, they use something called a mass spectrometer, and this is kind of a diagram of one. You have a sample gas that flows through the mass spectrometer, and you have a filament that actually vaporizes whatever sample you have, and you accelerate it through an ion beam past the magnet. So now, okay, if you have things that are different weights, and they're going to be deflected by a magnet, which one is going to be, or attracted by a magnet, which one's going to be moved more? The heavier one or the lighter one? The lighter one. So you can see how that curves up to a detecting screen. So in this case, they shot neon through there, and sure enough, neon 20 comes off here, neon 21 comes off here, neon 22 comes off here, so they know there's 3 isotopes of neon, and you can see there's different peak heights and areas, and what they do is they integrate the areas of each peak, and they figure out the percentages. You can kind of estimate that, assuming that all 3 of those peaks are triangles, calculate the area of the triangles, and you can figure out the percentage of each one. So they pretty much did that for all the elements, just how they got different atomic masses. So here they did oxygen, 3 isotopes, 16, 17, and 18. And there's their percentages, and those are their actual weights, 15.9949, 16.9991, and 17.992 AMU. So what is the average weight of oxygen? Again, you take the percentages, multiplying by their weights, and it comes up 16. Pretty close to 16. 15.9999 something. Questions? Okay. Let's go to ions now. An atomic ion, or monoatomic ion, is one that consists of just one atom with a positive or negative charge. If we lose an electron, here we see sodium, 11 protons, 11 electrons. Remember, they have to be equal. Atoms are neutral. If we lose an electron, then we have sodium with 11 protons and 10 electrons. So now it's got one more positive charge, and it becomes Na+. So that they call positive ions cation ions. If an atom absorbs or gains an electron, in this case chlorine gains an electron, it gets a negative charge. Those are called anions. I kind of wish you would have called them dog ions, but no, they're anions. So you see if you have sodium and chlorine, sodium ion is positive, chlorine anion is negative. Positive and negative particles attract. You end up with sodium chloride. So sodium chloride is a compound formed from 2 ions, so we call it an ionic compound. So an atom can lose or gain more than 1 electron. So again, I told you your periodic table has a lot of information. It turns out the elements in column 1 lose 1 electron. So I'm going to get +1. Column 2A loses 2. We'll skip all the transition. Column 3A, aluminum is 3+. 4, carbon is 4-. We'll kind of skip over carbon 4 right now, because 4 is like either gain or lose 4. But column 5 gains 3 electrons, so it gets a -3 charge. Everything in there. Column 6 gains 2, so it gets a -2 charge. Column 7 gains 1, so it's -1 charge. Column 8, noble gases, everybody's happy. Column 8 is the ultimate column. Everybody wants to be like the atoms in column 8. So now we look at the transitions. You can see some of these. Chromium is 2 plus, 3 plus. Manganese is 2 plus, 3 plus. Irons, they have multiple charges. That creates a problem. If I said I had a sodium ion, Na plus, sodium ion, you would know it's Na plus. There's no other choice. If I say you get a calcium ion, you know it's calcium 2 plus. That's in the second column. There's no choice. It's 2 plus. If I said you had an iron cation, which one? Uh-oh, now you got 2 choices. You have Fe2 plus and Fe3 plus. We use what's called the stock system of naming, STOK, which is Roman, we use Roman numerals. So Fe2 plus is called iron, and in parentheses 2, cation. Fe3 would be iron, 3 cation. So now you know, just by looking at the Roman numerals, what the charge is on the cation. Now in the older days, before the stock system, Fe2 was called ferrous, and Fe3 was called ferric. IC was for the larger charge, OUS for the smaller charge. It sounds great, doesn't it? 2 plus is OUS, 2 plus is IC. Works good. Copper, 2 plus. What is it? No, it's cupric. Oh, because IC goes with the higher. With copper, it's not 2 and 3, it's 1 and 2. You see where confusion can come in. For that, you have to know the charges. But with the stock system, you don't need to know. Copper 1, what's its charge? Copper 2, what's its charge? 2. So you have the Roman numerals, and it turns out if you look at manganese, it has like 3 or 4 different charges. All right? So what's that? Use the old way of naming things.
Cycle.
Fe2 plus is what? Ferrous. That's a Ferrous what? Ferris wheel. Good. So here they're talking about, again, the stock system. So you see manganese 2, 3, and 4. So you couldn't use OUS and IC because they only give you 2 choices. What do you put? You can say, well, the OUS is plus 2, 2 plus. The IC is the 4 plus. What do we call the 3 plus? Icus. And they're talking about the older nomenclature. I pretty much want you to use the stock system. How do you name ions? The anion is named by taking the stem of the element name and adding IDE. So chlorine becomes chloride, bromine becomes bromide, oxygen becomes oxide, so forth. Now, sure you can all read that. Can't read it. Polyatomic ions. Those are ions that are formed when several elements come together as a unit. What do you mean? NH4 plus, the N and the 4 H's are all one unit. Think of it as one thing. And the whole thing has a positive charge on it. That's the ammonium ion. Not to be confused with ammonia, which is NH3. This is ammonium. CO32 minus is carbonate. Now, there's a list of them. There's that table in your book. I wish I could tell you a way to figure out what they all are. If I could tell you how to figure out how they all memorize them. But our tests are open book, so you don't need to memorize them. You just need to know where the table is. But you need to be able to recognize them. So, this is the blow up of that table. You have carbonate, chlorate, chloride, chromate, cyanide, dichromate, dihydrogen phosphate, hydrogen carbonate or bicarbonate, hydrogen phosphate, hydrogen sulfate or bisulfate, hydroxide, hypochlorite, nitrate, nitrite, oxalate, perchlorate, permanganate, peroxide, phosphate, phosphite, sulfate, sulfite, thiocyanate. And that's just some of them. The more common ones. So we talked about sodium and chlorine. We said sodium wants to lose an electron. Get a +1 charge. Chlorine wants to gain one. So if you have the two of them together, that's great. On sodium, I want to get rid of an electron. Here's chlorine. Wants an electron. Oh, it's a marriage made in heaven. Here you go. Gotcha. Got my electron. Now I'm positive, she's negative. What happens? They come together. I can't write without it. Okay. So we form sodium chloride. And it's not a molecule. It's a formula unit. Splitting hairs here. But we end up with a crystal lattice where you have sodium ions surrounded by chloride ions and chloride ions surrounded by sodium ions. We have a cube. So this is Na plus, this is Cl minus, this is Na plus, this is Cl minus, Na plus, Cl minus, Na plus, Cl minus. So that's what's called a unit cell. That's the smallest part of the crystal lattice. So we just take a block like this, and we just keep stacking them. Eventually we get a small crystal, all the way up to a block of salt. If you've ever seen salt crystals under a microscope, they look like little cubes. And if you go on to 152, we'll actually talk about cubic or crystal lattice systems. Oh. I'm going to do a little stuff here before we go on to the next slide. So we know how sodium and chlorine go together. Let's talk about potassium. No, let's not talk about potassium. Let's talk about calcium and bromine. Calcium is in what column? So it's going to get a charge of what? 2 plus. When you enter it, the number comes first, then the charge, 2 plus. Bromine's in column 7, so it gets a charge of negative, -1. So remember, compounds are neutral. So I'm going to put calcium and bromine together. I got to come up with no charge. So here I am, calcium. I want to get rid of 2 electrons. There's a bromine. Here you go. I still got one I want to get rid of. He doesn't want it anymore. He already has this. What do I need? Another bromine. Okay, now I have what charge? 2 plus. He has negative. She has. So we have 2 negatives and a 2 plus. What's going to happen? They're all going to come together. So the formula is going to be CaBr2. Okay? Well, aluminum, what charge? 3 plus. Sulfur, 2 minus. So the aluminum wants to get rid of 3 electrons, right? Sulfur wants to get 2. So here's the 3 electrons. Okay, I get rid of this one to the sulfur, this one to the sulfur. Sulfur's got its 2, I still have 1 left over. What do I need to do? I need another what? I still got to get rid of electrons. I need another sulfur. There, I got rid of my electron. Wait a minute, this sulfur wants another one. So now I need another what? Aluminum. Okay, this one's got it. Okay, now that sulfur's happy. Now I got aluminum with 2 electrons. Now what do I do? Another sulfur. Okay, that sulfur's got its 2. The aluminum got rid of its 3. What is the formula for the compound? Al2 S3. I have to go through that for every single freaking thing I do. Oh, I'm recording it, so freaking. Okay. Al 3 plus, sulfur 2 minus. Now I'll take that 3 and I'll put it here, crisscross it, the 2 down here. Al2S3. There. That was a lot quicker. That's it. In a nutshell, that's how you do it. So there's aluminum oxide, which is the same as aluminum sulfide. Why? We did aluminum sulfide, they did aluminum oxide. Why did they come up with the same? Same charges. What about sulfur and oxygen? Tell me something about it. On a periodic table. They're in the same column. Here we have calcium. Notice we have phosphate. So that's polyatomic ion. You look on your table. If you hadn't memorized it, phosphate is 3 minus. So we crisscross again. Now you see how we have Ca3. We have the PO4 parentheses with the 2. You have to have the parentheses. Because the PO4 acts as 1 unit. That whole PO4 has 3 minus charge. So looking at calcium phosphate, how many calciums do I have in it? How many phosphoruses? 2. How many oxygens? 8. The subscript outside the parentheses multiplies everything inside the parentheses. I have 2 PO4s. I have 2 P's, 8 O's. Okay? So let's talk about naming ionic compounds. So, ionic compounds consist of a metal and a nonmetal, or the ammonium ion. The anion can either be a monatomic anion or a polyatomic anion. So if a cation has only one charge, one possible charge, you name the metal first. So let's look at Ki. K is the metal. We name it first. We use the name of the element. So this is potassium. For the anion, monatomic anion, we use the stem and IPE. So this is potassium iodide. Now, if you have FeCl2, FeCl3, remember iron can have more than one possible charge. So we have to use the parentheses, the stock system. So I'm going to put, they're both going to be an iron chloride. What's the charge on the iron here? Is it 2 or 3? Okay, a couple ways to figure that out. Chlorine is what charge? -1. How many chlorines do we have here? So we got -2 here. Compounds have to be neutral. So if there's -2 here, how many positives do I need? Okay. How many irons do I have? 1. So its charge has got to be 2+. Down here, again, chlorine -1. So here I got 3 negatives. To neutralize that, I need 3 positives. So iron on the bottom one has to be 3+. Or I could just take the subscript and go back up the opposite way. So I can, top one, FeCl2 is iron 2 chloride. The bottom one, FeCl3, is iron 3 chloride. Now, if you have a polyatomic ion, we know this is a polyatomic. We have sodium, NaNO3, sodium. NO3, if you look in your table, is nitrate, NO3 minus. So it's sodium nitrate. Okay, so let's practice some here. And let's just do MgBr2. What would its name be? Magnesium bromide. Remember, always has to end in IDE. It's not magnesium dibromide. We don't use any prefixes. It's magnesium bromide. CaSO4. Calcium, SO4 is a polyatomic ion. That's all octagon. You gotta look at the table. Look at the table. I forgot what page it's on in your book. It's sulfate. It's calcium sulfate. I'm going to use that to show you something. If you do, calcium we know is 2+. Sulfate, if you look it up, is 2-. Remember I told you about crisscrossing to get the formula? Well, if you crisscross this, then you get Ca2SO42. When you do formulas, you have to use the lowest form. So those 2's can each be divided by 2, so it's CaSO4. Calcium sulfate. So if you do the crisscross, make sure those two numbers can't be reduced. Oh, what else we got here? Let's see. Al2Se3. Start with the cation, which is the metal. What's the metal? Sc is what? Selenium, so it would be, yeah, it's a little tough to say. Selenide. Aluminum or aluminum selenide. Again, practice some of the web links, and the first web link on chem nomenclature doesn't work. But if you go down to the help in all areas, you can find chem nomenclature. Practice these. After a while, it becomes second nature. Let's see if you're awake. Name it. PaNa2. Yeah, it's two metals. So does it exist? I can find it in grocery stores. PaNa2. Banana. Thank you. Oh, he's so funny. Okay. The other one I have, I don't think you'll get. You're too young. Hio silver. Okay. Lone Ranger. Google it. Okay.
I made a remake recently.
Yeah.
It wasn't very good.
No, I saw it and I agree. It wasn't very good. So, name MgO. Magnesium oxide. Very good. AlOH3. OH is a polyatomic ion, so you need to use that table in your book. Or from the PowerPoint if you print it out. Aluminum hydroxide. Where do we find it? You all probably used it today. I hope.
Yeah.
Deodorant. Thank you. That's the antiperspirant part of it. Fe2SO43. No, moon, white. Well, you got the iron part right. You got the sulfate right. Remember, iron has multiple charges. What's its charge here? Yeah. Yeah. Iron 3 sulfate. How did you figure that out? Well, SO4 is -2. And we have 3 of them, so that's -6. To make it neutral, I'm going to have +6. I have 2 irons. Each one's got to be 3+. Iron 3 sulfate. If you have a transition metal, you can pretty much guarantee it's going to have multiple charges. Couple exceptions, silver is one, silver is only +1. So, going from the name to the formula, mercury 1 chloride. Well, there's all the cations and anions. So how is that mercury and chlorine going to go together? We have Hg2 is 2 plus, Cl minus. What do? Crisscross it, so we're going to end up with Hg2 Cl2. Lead plus chromate 2 minus. How are they going to go together? Cancel out the charges. Yeah, 1 to 1. PbCrO4. And potassium hydrogen phosphate. So again, potassium hydrogen phosphate. You look up in your table, 2 minus. How are they going to go together? Potassium is +1, by the way.
2 comes down on the K.
Okay, so K2 HPO4. Right, this down here, this over here. You do one here. Sodium's what charge? +1. Hydrogen carbonate is -1, so how are they going to go together?
Cancel out.
Yeah, so they just go straight together. NaHCO3. Sodium hydrogen carbonate. Where do we find that? I said sodium bicarbonate. Sodium bicarbonate, you all have it in your house. Some of you have it in your cupboard, some of you have a box of it in your refrigerator. Baking soda. Oxoanions. What's an oxoanion? They're polyatomic ions that contain 1 or more oxygens and 1 central atom of another element. So here we have chlorate, nitrate, and sulfate. What that means is in chlorate, the Cl is surrounded by oxygens, in nitrate, the nitrogen is surrounded by oxygens, and in the sulfate, the sulfur is surrounded by oxygens. So there are some rules for naming these. First of all, you have to figure out which one of the forms is the 8 ion, the ATE. If you have 1 more oxygen than the 8 ion, it's called the per-8 ion. So ClO3 is the chlorate ion, ClO4 minus is the perchlorate. If it has 1 less oxygen than the 8, it's called the ite ion. So ClO3 minus is chlorate, so ClO2 minus is chlorite. The ion with 2 fewer oxygens is the hypo. ClO minus is hypochlorite. See how easy that is? That's why, look at the table. I was being sarcastic, it's not that easy to remember. Because, guess what? the Cl03 is not always the 8 ion. Or the O3 is. So here you have BrO4. Well, it turns out BrO3 is the 8 ion, so BrO4 would be, it has one more, you make it per, right? It's going to be perbromate. CO3 is the carbonate, so HCO3, which wasn't covered in the previous rules because we were only talking about adding oxygens. Here we stuck H in there. It's the hydrogen carbonate or the bicarbonate. The SO4 is the sulfate. You would think it'd be the SO3, but no, we changed it to the SO4. So now the SO3 is one less than the H, so the SO3 is the sulfite. See how easy that is? No. So use the table. Hydrates, those are special compounds. The ACO2, see that little dot, does not mean we're multiplying it. That's not a mathematical thing. That means there's water associated with the compound. In the picture up there, the blue crystals are copper sulfate pentahydrates. It has 4 molecules of water associated with it. If you heat it, you can drive off those 5 water molecules, and it will turn to be a white powder like that, which is called anhydrous copper sulfate, anhydrous meaning without water. Now, if you leave it sit there in the open, it will absorb 5 molecules of water and turn back to blue. We may actually do that experiment this semester. So all kinds of hydrates, magnesium sulfate, pentahydrate. Anybody know what that is? Get at the drugstore. Probably some grocery stores. Probably know it as Epsom salts. Okay. Enough of ionic compounds. We're going to move on to molecular formulas and molecular compounds. So a molecule is a combination of at least 2 atoms in a specific arrangement held together by electrostatic forces known as covalent chemical bonds. So, let's see if I can explain that. Hopefully fairly easily. So here I have hydrogen. How many electrons in hydrogen? 1. Okay. Here's. So hydrogen doesn't exist as H. It exists as H2 in nature. I'm going to go over here. I'm a hydrogen atom. I have 1 electron. So you're a hydrogen atom. You have 1 electron. Remember I said atoms want to be like noble atom closest to it? What's the noble gas or noble element closest to hydrogen? Helium. How many electrons in helium? 2. So the hydrogen atom wants 2 electrons. So you want 2, you have 1, you need how many? 1. Thank you. Here you go. So now you have 2, you're happy, right? Just like helium. What about me? So bad. I want 2. Now I got 2, I'm happy. What about him? Yeah, he's not happy. How can we both have 2? Grab that again. See, now we're both sharing. So part of the time, he's got 2, part of the time, I got 2. Think of it as joint custody. Okay? So that's a covalent bond. This is considered to have 2, and this is considered to have 2. So covalent is sharing of electrons. So the ones that exist as diatomic molecules that you need to know, besides hydrogen, nitrogen, oxygen, and the halogens, fluorine, chlorine, bromine, and iodine. So if you remember that, because when later on we start writing equations, if I say hydrogen plus oxygen gives you water, and you say H plus O gives me H2O, you're wrong. It's H2 plus O2 goes to H2O, and then we have to balance it. If you don't get it right, if you forget their diatomic, you get it to doing stoichiometry, balancing equations, you're going to get so messed up, you don't know what's going on. So remember those. So if both atoms are the same, it's called homonuclear. If they're different, we have heteronuclear. And if we have a whole bunch of them together, it's polyatomic. So like HCl, both nonmetal, oh, by the way, covalent, are two nonmetals or a metalloid in a nonmetal. Okay? You see a metal, ionic. You see two nonmetals, covalent. You see a metalloid and a nonmetal, covalent. So HCl, two nonmetals, that would be heteronuclear. Methane, CH4, would be a polyatomic. We have four hydrogens sharing electrons with carbon. So a chemical formula denotes the composition of the substance. A molecular formula shows the exact number of atoms of each element in the molecule. Now remember we called ionic compounds, they don't form molecules, they form formula units. Remember when sodium and chlorine came together, we had this crystal lattice built up. Well, covalent compounds, when they crystallize, sugar, obviously you can get crystals of sugar, you can go to store, it says right in the box, Dixie crystals, crystals. Ionic compounds at each lattice point, each corner of that cube was an ion. In molecular crystals, each corner, what they call lattice points, is the whole molecule. So if you think of sugar as C11H22O11, C12H22O11, each point would have C12H22O11 at it. That forms the crystal there. There's also a term you may run into called allotropes. Two distinct forms of an element. So carbon actually has three allotropes. It's not listed up here. One, of course, is diamond. Yay, diamond. Okay. First one. Other one is graphite, where the carbon crystallizes in sheets that slide over each other. So graphite is a very good lubricant. You can go to Home Depot and buy little bottles of powdered graphite. You get locksmith sticky, you squirt it in there. The advantage with that is if you use a liquid lubricant like the silicone spray, it attracts dirt and dust and gums things up. Graphite doesn't do that. Now, if you don't want to buy the graphite at Home Depot, you have a source of graphite at home. Yeah, number 2 pencil. Take your key, rub your number 2 pencil up and down and get it all pencil-y. Pieces of graphite, stick it in the lock and wiggle it around. That should loosen it up. Third form is called Buckminster fullerene. You know what that form is? It's 60 carbon atoms. Anybody know who Buckminster Fuller is? Famous architect. Well, apparently not too famous since nobody knows. He designed geodesic domes. Everybody know what geodesic dome is? If you think of Epcot Center, that big white, that's a geodesic dome. Or soccer balls. If you think of a soccer ball is not really round. If you look at it closely, it has little 5-sided panels that are all stitched together. That's how that carbon crystallizes. Very sturdy, stable structure. Geodesic domes are very sturdy. He wanted to design houses, and he actually did build some houses that way. They're extremely sturdy. You can't hang a picture anywhere because there's no flat walls, but it's extremely sturdy. Okay? So they named it after him. And he talked about nanotechnology, he talked about carbon nanotubes, and it's all done with what they call buckyballs, short for Buckminster Fullerene. So we can look at more molecular formulas in a couple ways. The structural formula, we can look at H2O. H2O, now if you look at it, it says, well, how is that arranged? Is that HHO, HOH, OHH? You don't know, just from H2O. Second one, HOH, tells you how they're arranged. So you know you got a central oxygen with a hydrogen on each side. The third one down, those are single bonds. The fourth one down tells you that its shape is actually bent. And the last one at the bottom is what's called the space filling model. That tells you, if you think of the size of the atoms, the oxygen atom is a lot bigger than the hydrogen atoms. So that's what it would look like in space, three-dimensional space. There is the ball and stick model for ethanol. I assume you all know what ethanol is. It's added into gasoline, and it's also alcohol. So what was the, okay. Ball and stick model. Carbon is black, hydrogen is white, oxygen is red. So what is the formula for this? Well, here are the three. How many carbons do we have? How many hydrogens? 6. How many oxygens? 1. So that would be the molecular formula for ethanol. It's not the way an organic chemist would write it, but that's still the molecular formula. How do we name these? Completely different than we do ionic compounds. So binary molecular compounds consist of 2 elements. We first name the element that appears first, and then the second element, again, we change the ending to IDE. So HCl is hydrogen chloride. SiC is silicon carbide. Simple enough. All right. We need to know some prefixes. What's the prefix for 1? Mono. 2. Di. 3. 4. Use with a T. Tetra. 5. Penta. Pentagon. 6. Hexa. Hexagon. 7. Hepta. 8. Octa. 9 is nona, N-O-N-A. 10. What? Deca. Deca. Can't hear. Oh, man, there we go. So, CO is carbon monoxide. CO2 is carbon dioxide. SO2 is sulfur dioxide. SO3 is sulfur trioxide. NO2 is nitrogen dioxide. N2O5 is dinitrogen pentoxide. Pretty clear, isn't it?
Makes more sense than how you can name
Yeah, it does. That's why I like more. So let me just go here. N2O5. Remember we said 5 was penta, right? So why isn't it pentoxide? The one rule you have to remember is when you have 2 vowels that come together, you get rid of the first one. Pentoxide. dinitrogen. There's 2 there. If the first one, like for CO or CO2, the subscript is 1, it's not, you don't use mono, so it's not monocarbon monoxide. It's carbon monoxide. Okay. Several years ago, a bunch of college students wrote to the congressman saying something has to be done about this chemical. We're worried. This chemical is known to kill more people every year than any other chemical known. Toxic. It kills people. We need to take steps. Monitor it. Compound is dihydrogen oxide. Congressman actually set up a committee to study the effects of dihydrogen oxide. Until someone pointed out dihydrogen oxide, what's the formula? H2O. Water. And water does kill more people every year than anything else. People die in tsunamis, and floods, and hurricanes, and everything else. And they kind of made a laughing stock out of Congress, showing that they didn't know any chemistry. NF3, what is it? Name it. Nitrogen trifluoride. N2O4. Dinitrogen. Not tetroxide, tetroxide. You gotta drop the A. Dinitrogen tetroxide. Okay. So given the name, you should be able to write the formula. Given the formula, you should be able to write the name. So if I said nitrogen monoxide, you tell me the formula is? No. Nitrogen monoxide. No.
Yeah, that's one.
Leave.
NO. No. Yes. No is correct. Sulfur tetrafluoride, what's the formula? SF4. Hey. Tetraphosphorus decasulfide. P what? S what? There you go. Electric compounds are easy. You don't have to write multiple charges. You don't have. You just have to know those prefixes for binary. Some molecular compounds we don't use technical names. We use the everyday names. SiH4 is silane, NH3 is ammonia, PH3 is phosphine, H2O obviously is water, H2S is hydrogen sulfide. Tell me about hydrogen sulfide. Anybody know? You'll know. You have some. It is the smell of rotten eggs. Okay? So that's what eggs when they rot. That's the smell they produce, hydrogen sulfide. Okay? Oil well fires also produce hydrogen sulfide. Think about hydrogen sulfide, it's very toxic. So when you're smelling it at low levels. If the levels increase, it gets so, physical properties for smells, it overloads your sensors, it stops smelling, you can't smell it. So it used to happen in early oil fires, the guy would walk towards the fire and smell hydrogen sulfide. And it stinks. But you take a couple more steps, concentration increases, you don't smell it. Ah, it went away. Take a couple more steps, fall over and be dead. Because you got exposed to too much hydrogen sulfide.
So,
Okay.
rotten eggs produce hydrogen sulfide,
How do you rotten eggs produce hydrogen sulfide?
so you could potentially kill somebody with a
No, you have to bury them in the rotten eggs, and then they die from the weight of the eggs before that. Maybe we'll do an experiment where we produce hydrogen sulfide. We used to do that all the time in chemistry. You can always tell when the chemistry department was doing that experiment. The whole building would smell like hydrogen sulfide. If you've ever walked by a sewer or a drain where you haven't used it in a while, the trap dries out, you can smell the sewer gas. Okay? Or some people produce it if they eat certain foods. High sulfur foods. 2 or 3 lunches at Taco Bell. You'll know. Okay. Because methane, the other gas you produce, is odorless. So. Acids. An acid is a substance that produces hydrogen ions when dissolved in water. Hydrogen ions are also called protons because H+ means we've lost an electron. Hydrogen is 1 proton, 1 electron. If you lose the electron, you're only left with a proton. So, same chemical formula can have 2 different names. Can we make it any harder? HCl is hydrogen chloride. Hydrogen chloride by itself is a gas. If you dissolve it in water, it's hydrochloric acid. How do we name that? We take the hydrogen, change it to hydro. The chloride, we changed it to IC, so it now becomes hydrochloric acid. Anybody know where you can get hydrochloric acid? Well, it's kind of hard to get it out of there, but people who binge purge, that's how they rot their teeth. Hydrochloric acid dissolves the minerals in your teeth. Obviously, you can get it in the works because I did the lab demonstration right with the egg. Okay. So then if I want pretty pure hydrochloric acid, I can go to Home Depot. What? Drano is just the opposite. Anybody heard of muriatic acid? People that do masonry work and lay bricks and that, they have the mortar, and the mortar gets out on the bricks. To clean it off, they use muriatic acid because it dissolves stuff. So if you use it, you can get it at Home Depot. They call it muriatic acid. Be very careful. Wear gloves, rubber gloves, aprons. So HF is either hydrogen fluoride or hydrofluoric acid. We did hydrochloric, we have hydrobromic, hydroiodic, and hydrocyanic acid. Hydrogen cyanide is a gas. Supposedly it smells like bitter almonds. But if you smell bitter almonds and it's hydrogen cyanide, don't worry, because you did it. God, he keeps telling us stuff that kills you. Okay. So what they do in the gas chambers is they take sodium cyanide, which is a salt, usually in pellet form, they dump it in the beaker, they add hydrochloric acid in it, and release hydrogen cyanide gas. You're sitting there, eventually you have to breathe, but not for long, and it kills you. Oxoacids can produce hydrogen ions again, and oxo anions, which are anions which contain oxygen. So there we have nitrate, sulfate. In water, we get nitric acid, my favorite acid, and H2SO4 sulfuric acid. Where do we find sulfuric acid?
Atmosphere.
Yeah, but I mean in large quantity. Y'all brought it with you today. Not in here. It's out the parking lot. That's the acid that's in your car battery. So, you know, if your car battery dies or that, you open it up and it's leaking, don't just pick it up with your hands. Put on some rubber gloves. Nitric acid, I like that because it heats copper real well. And if you're a hungry graduate student in the middle of the night, all you got is like 4 or 5 or 6 pennies. You can put them in a beaker, add some concentrated nitric acid in a fume hood because it releases toxic fumes. And if you leave it just the right amount of time, it heats the penny evenly. You take it out, it's now the size and weight of a dime. It works just fine in a vending machine. Statute of limitations are over, so don't report me to anybody. Okay? And again, we go through the whole thing. HCl3 is chloric acid. If it's 1 less oxygen, it's chlorous acid. And if it's 2 less oxygens, it's hypochlorous acid. And I think people are leaving, so we're going to stop there. Here's my thing.